Happy Friday, everyone. I'm glad that it's going to be weekend soon. So what we're going to cover today is an example problem that involves finding a factor of safety against fatigue, assuming that we want infinite life for a connection that is welded. Okay, and you can see the picture of the specific problem that we're going to work there. It does have weld groups on both sides of the little tab that protrudes right here. Okay, it says right here, welded both sides. We're given some dimensions of this connection, so we know how wide the tab is right there, and we know how tall the tab is. The tab is there to provide an attachment point for a spring that is then going to be extended to a crank that is rotating. Okay, so that's what's going on here. We have this spring with a spring constant of 200 pounds per inch, and the end of this spring, which in the position that it's shown right now, it's shown with the spring having no tension in it, so this is the free length, as we call it, of the spring. But we're going to stretch it an inch to attach it to this crank, and then the crank has a radius from its center of rotation to that attachment point of 2 inches. Okay, and what's going to happen then is, we're not saying what this particular mechanism is for, but then the crank is going to turn around, and as a result of turning around, it's going to put a variable force in the spring, and then that spring is going to transmit that variable force back to the tab, which is held by the weld. And what we're concerned with for this problem is the fatigue, the susceptibility to fatigue that might happen in that weld. All right. The materials that are involved there are 1018 steel. Okay. And we're going to assume that the strength in the weld is going to assume the properties of those parent materials, which are 1018 steel. A few of the assumptions that I'll go ahead and talk through right now. The first one on there is very important. We are going to neglect torsion effects. What do you think that means? Okay. Yeah, so we're assuming, based on the dimensions of this shape, that primarily the type of stress that we're inducing in the weld is due to kind of a flexure around this blue line that I'm showing right here, which is the neutral axis. Okay, so this little line right here, that is the neutral axis. With respect to bending, we're saying that primarily the stresses that are induced are due to, I would say, bending as well as maybe direct shear that happens, primary shear that happens in that weld group. And what we're doing here is we're ignoring the possibility that there could be some slight little distance from where this force is applied back to maybe the center point, center axis of this whole weld group, right? I could find the centroid of the weld group would probably be somewhere in there. And so if I have a distance from that axis relative to where this force is applied, then ostensibly that would create some small amount of torsional stress in those welds. What I'm saying is, let's neglect that. Maybe this distance is really small, meaning that we can neglect that effect. Other things that you can do if you're trying to force an effect like that to be negligible is you can affect the shape of your tab and create a situation where the line of action of the force actually does lie right over the top of an axis that passes through the centroid of the weld group. Does that make sense? So either way, let's, for this example problem, say we're going to neglect that torsional stress just so that we can focus on what's probably the main effect, so that we don't end up in the weeds trying to solve all kinds of different things before we do the fatigue problem. Okay, other assumptions that we'll have here, I already mentioned the weld will assume properties of the parent material, and then I put in parentheses there, let's assume that it's like an annealed material, all right? Or another way to do this is talking about like a hot rolled material. In either of those cases, those are two states of material that tend to be close to no added strength due to things like heat treatment or cold working. So we're going to assume that. So we're going to assume room temperature. We're also going to assume we only want 50% reliability, and we want infinite life. We're going to evaluate both with and without our stress concentration factor with respect to first cycle yielding. The reason I do this both ways is that on occasion, maybe it is important to consider your stress concentration factors. When might that occur? What would be, it may not be something we have to, or we should be thinking about necessarily on this problem, but what would change perhaps relative to this problem that might make us really want to make sure we evaluate first cycle yielding, including the stress concentration factor? Can you think of something? Okay. What if this material was more brittle? Okay, this is not a brittle material, but if it was more brittle than it is, then that would be a situation where I would probably want to be careful and go ahead and include that factor. Anyway, we'll do it both ways, so you see how to do it one way or the other, but we'll go ahead and mention that here, that you may or may not need to apply that depending on the situation. Okay, the other assumption that we'll make to simplify this a little bit is that we're going to ignore little changes vertically in the line of action of this force. In other words, as this spring is attached to this crank, it can actually deviate a little bit up and down angularly due to where it's attached to that crank. And I'm saying let's ignore that. Let's take the primary amount of force that we're going to have to deal with to be purely horizontal. One other justification I can make for that force, or excuse me, for that assumption, is that when we attach the spring like this, what we're caring about most probably for our fatigue question is the maximum stress that is induced and the minimum stress that is induced. Where do you think the crank will be located where the maximum stress will be induced? 180 degrees from where it's shown right now, right? That'll be where it's stretching the spring the farthest. And so we're going to evaluate that point, and it's likely that even though we might have small vertical components that exist in the welds in between max and min, it's likely that that won't have an effect on what the actual max and min stress are in the weld. Okay? So that's what we're going to do. We have a few steps to do here. Let me actually do this. And a lot of times when there's a bunch of steps that have to be completed, I like to do this at the very beginning to help guide what our thought process is. And this is what I'm going to do now, is put our equation for fatigue strength, or excuse me, for fatigue factor of safety that we get back from Chapter 6. I'm going to get that equation and write it up here very first thing so that we know what we're shooting for. And that way we can figure out how to solve for each of the individual pieces. And so let me go ahead and do that here. N sub f, okay, I'll just write this right here. N sub f using the Gerber criterion. This is on page 315. Okay, and it's in table 6.7. Okay. N sub f is going to be equal to 1/2 of, here it says S sub ut over sigma m, okay, times sigma a over S sub e. All this times -1 plus the square root of 1 plus 2 times sigma m times S sub e, all this over S sub ut, sigma a, and then everything in that fraction right there is squared. Okay. I think I've got that written down properly. All right, this is going to guide our process of working this problem. What are some things that, you know, when you the very first look that you get at this equation, there should be something that kind of stands out to you very first thing. What do you think that might be? Okay. What'd you say? Okay, it does say that your mid-range needs to be greater than 0. Where we are going to be evaluating this, our critical point is basically going to be right back here. All right, that's where our maximum tensile stress is going to be in the part, and so it will actually have a mid-range stress greater than 0 at that point. So we're good in terms of using this equation. Okay, but that's not really what I was driving at. There's another thing that should kind of stand out to you. Let me give you a hint. Whenever we're evaluating stress in welds, what kind of stress have we always been computing up till now? Shearing stress. Okay, so this is something that we need to account for here. This equation where it has parameters like S sub ut, what kind of a strength is that? That's a tensile strength. Okay, and so the very first thing that I'll do is say that there are a few conversions that we need to do on an equation like this. One of them is for any place I have S sub ut. In chapter 6, there's a way that you can calculate S sub su. Okay, that is one of the things that it has in there, a way to estimate what your ultimate strength is for the purposes of fatigue, based on S sub ut. What else do we need to change, you think? Okay, let me say for SE, this one's kind of interesting because I'm going to say we need S sub SE. Okay, but the way we end up with an S sub SE is actually by applying the proper loading factor. That's one of the Marin factors that we had from chapter 6, and you might remember it where we multiplied by 0.59. Simply multiplying by 0.59, the main job of that parameter is to turn it into a shearing strength rather than a normal strength. So that's another thing that we'll have to do. And so S sub ut here and S sub e right here would also be subject to those conversions that we're going to need to do. All right. We'll get to those here in just a second. But what else do we need to do? Okay, the stresses are going to be shearing stresses. All right, so we're going to come up with a tau sub m and a tau sub a. Okay. So it's basically the same equation, but we're going to need to convert and all of these different terms to be shear terms rather than being normal strength and stress terms. Okay, so this is our basic equation now kind of corrected for our particular case. And there's a few different places where we can start working on this. And I'm going to suggest, why don't we start with the things that are most peculiar to welding, right? Because there's a few steps of this that aren't necessarily going to have to be directly related to welding. So what do you think I might be referring to there? Okay. To find tau sub A and tau sub M, these are the stresses that are felt in the weld, right? These are mid-range and alternating stresses that are felt in the weld. In order to find those, first what I need to do is find maximum and minimum stresses that are held in the weld at the critical location. Okay, and just a few seconds ago, I identified the critical location being right back here. Okay, so that's the critical location right back at that end of the weld. How do you think I know that that's the critical location? Why do you think I'm picking that out as being critical? Okay. Yeah, I mean, for one thing, it's the furthest away from the neutral axis, right? It represents one of the furthest distances from the neutral axis. So that means my flexural stress is going to be highest that's furthest away from that axis as possible. Why do you think I don't necessarily look at this end, even though all the calculations might end up being very similar at that end? Why do you think I'm not looking at that end? Okay, because you have bearing stress that's probably helping you out on that end, and so if there's going to be a failure, it's less likely that it will happen on that end than it will be on the end that I've identified. So that's our critical location, and we need to know what are the maximum and minimum stresses that are felt at that location. So how do I get that? Okay, I need to handle positions 1 and 2 for the spring. I'll go up here and do that. Position 1 of the spring involves stretching it by 1 inch. And I'm going to call that, say, F min. Okay, so F min ends up being 200 pounds per inch multiplied by what? 1 inch. Oops. 1 inch, which is just going to be 200 pounds. What about F max? Okay, 200 pounds per inch times, and here I'll have the 1 inch that I had to stretch to first put it on there, as well as another 4 inches because it's going to go from the radius pointing toward the spring attachment to the radius pointing away from the spring attachment, which is a difference of 4 inches. So that all adds up to 5 inches. Okay, and so what does that give me? 1,000 pounds. Okay, so those are my maximum and minimum stresses that are felt, or excuse me, forces that are applied to the top of this tab. All right. What do I use those for? Okay, I can now calculate stresses that are induced in the weld group. Okay, and for that, I probably want to evaluate primary and secondary shear. Okay, for primary shear, it's fairly simple. All you do is you take the area of the throat of the welds, and so to get that area of the throat of the welds, you go to table 9.2, and I'll point out here something real quick. Remember, for table 9.2, it put this footnote on that table that said that each of these groups of welds, you assume that the moments are being applied about a horizontal axis through the group shape that you see there. Okay, and so when you look at this table, I would say, if you weren't being very careful, there's actually 2 candidates that might be attractive to you in table 9.2 for the weld groups. What do you think those 2 groups might be? Okay, if you're looking at table 9.2, there's basically 2 entries where there are 2 parallel lines. And that's what we have, right? We have parallel lines of weld applied here. How do you know which of those 2 to pick? So we're looking at cases 2 and 3. So my question is, what axis is the moment being applied around? Okay, it's being applied around that neutral axis I identified just a few seconds ago, right? That's basically right here. When you pull with that force of F, it creates a moment applied around that axis, and so that axis would be oriented according to how case 2 is in the table. Okay, so you want to be careful and make sure you're appropriately matching the cases in the table to the cases that you actually have in your real problem. All right, so for primary shear, now that I know that I'm on case 2, my area is just 1.414 HD. Okay, so the stress that I then have is equal to that applied force that I have, and that I probably need to do this 2 different times, right? Need to do this for my minimum. Okay, the minimum there is going to be 200 pounds divided by the area that I have, which is 1.414 times H. Okay, I believe I had that on here earlier. These are 1/2 inch welds, right? That's my weld size. So I put 1/2 inch, and D is the length of one of these welds. Okay, and so that would be 1.75 inches according to this piece of information right here. Okay, and so that ends up giving me 161.65 psi. Okay. I'm going to highlight that so it's easy to find later. All right. Then what? Okay, we can do primary shear at the maximum end of the scale, or when the spring is stretched to its maximum. So that'll be 1,000 pounds over the same denominator. Okay, and when we plug that in, it ends up giving us 808.24 psi. Okay, so there's primary shear. That's kind of the slightly easier part, although secondary shear is not that bad either. Okay, what do I need to do for secondary shear? Okay, maybe the first thing to do is to find my I value, my moment of inertia value there. Moment of inertia, second moment of area is a more appropriate term for it. But to do that, I need to know what the I sub u, the unit second moment of area is. And so we look at, again, table 9.2, case 2, and it gives you for that weld group, I sub u is just equal to d cubed over 6. Okay, so d cubed, so the d that we have for this was 1.75. Okay, and this gives me 0.8932 inches cubed. Okay, and remember, this is basically, it eliminates the weld size from consideration, and it just basically accounts for the geometry of the weld group itself, like how the welds are laid out. To get the overall second moment of area, you have to take this and multiply it by, there's an equation on the previous page that is labeled C. It doesn't have a number to it, but it's labeled C on page 479. And you just multiply by 0.707 times the weld size times I sub u. Okay, and when I punch those in, this ends up giving me 0.31576 inches to the fourth. Okay. All right, so that's one of the parameters that I'm going to need. I guess I'll put some labels up here. This is equation C on the previous page. All right, my I sub u equation came from table 9.2. Okay, so we've got those. Now what? The equation we're going for is MC over I, correct? So that is the, we need to probably do two of those, right? We need to do a maximum and a minimum for the two different force values that we're considering for the maximum stress of the stretch of the spring and the minimum stretch of the spring. So I'll start with minimum. Okay. MC over I. So M is what? Okay. Yeah, the height from where the weld is located to where the force is applied is 3 inches. And so I basically take the force of 200 pounds and multiply by 3 inches, and that gives me my moment. Okay, so those two terms are M. C, what's C? Okay, half of the 1.75 inches. And then I we just found, so we just plug it in, 0.31576. Inches to the fourth. Okay, now a note that I want to make right here at this point is that what I just calculated right here does not yet take into account stress concentrations. Okay, so I'm just going to put that over here. No K sub Fs yet. That's just reminding me that that's something I still need to do, but I'm going to go ahead and leave it like that for right now. Okay, so that's one way of thinking of this is your minimum nominal stress. Okay, all right, now my maximum. Same idea. The only thing that changes is we go to 1,000 pounds instead of 200 pounds. Okay, and so with those two equations, we get that our minimum, I'll do that one first, minimum shearing stress is equal to 1,662.7 psi, and my maximum is 8,313.3 psi. Okay. All right, so now we have our primary shear and our secondary shear values for max and min all computed. What do I need to do with those? Okay, I need to combine them into kind of an overall stress at the minimum stretch of the spring and an overall stress at the maximum stress of the stretch of the spring. Okay, now here is one nice way to do that and include your stress concentration factors at the same time. Okay, so I'm going to say, by the way, it's probably better for me to go ahead and put some markers on here to indicate this is primary shear and that these are secondary shears. Neglected to do that earlier, but that's probably a good way to note that so that when I get down here and say for my minimum stress, okay, and for these bending cases, what's the equation we use? Okay. All right, we were going to use the square root of the sum of the squares. This is based on equation E on page 479. Okay. So we're going to take our minimum stress that we have here, 161.65 psi, and before we square it, we're going to multiply this by our stress concentration factor that is most appropriate for the type of stress that we see for that primary shear. Where do we get that? Okay. Yeah, there is a table in the book that gives you some guidelines for what you might think about using for some stress concentration factors. And it gives it to you there by the name of the different kinds of welds. One of them says reinforced butt weld. One of them says toe of transverse fillet weld. Okay. One of them says end of parallel fillet weld. All right. And the last one says T-butt joint with sharp corners. Okay. Which one of those do you think applies most appropriately for what we have in this case? Okay. We're probably talking about end of parallel fillet weld, right? Because what you have here is that the welds are parallel with the direction of the applied force. They are fillet welds, and we're looking at the end of them, so it looks like that's a good estimate. And it tells you there that it's going to be 2.7 is a good estimate for that stress concentration factor. Okay. That's on page 482. Okay. We'll say this 2.7 right here, this comes from table 9.5 on page 482. Okay. And then to this, I'm going to add the secondary shearing stress for minimum spring stretch. I don't know why that's so hard for me to say. 1662.7 psi. Now for this one's a little more tricky. Which of these descriptions of types of welds do you feel like would be most similar to the type of situation we have shown up here? This one's a little trickier. Okay. Well, it's not the same as the one before it because the direction of the stress that we are accounting for with this secondary shear is, what we did the first one, the direction goes this way. That's the direction of the stress that we just handled for the parallel to the fillet welds factor that we just came up with. Well, what direction does the stress go due to bending? This way, right? So this is the primary, and this is secondary. Okay, that's the axis along which the stress would act if we were counting for the secondary shearing stress. Well, now that you know that's the direction that the stress is acting, and we're looking specifically at the end of this weld, does that give you any hints about which of the types of stress concentrations in table 9.5 we should maybe think about more closely? And let me give you a little hint here. Okay, if you have a T-butt joint, what that means is that you have a piece of material that's welded something like this relative to another piece of material. Right? Something like that. And it means that you're pulling on it like this relative to this piece of material where you're pulling on it like this. Okay? What direction of stress is induced in the welds that exist right here? Right? What direction of stress exists in those welds? Do you agree that the direction you're pulling on it will tend to stress the welds in this direction? Okay. Well, that's the same direction of stress that we have due to the secondary effect that's going on over here on this tab. And so this is my justification for why, if it was me and I was working this problem, I would look at this and say, I think the closest situation that I have from the information that's given in this table is something similar to a T-butt joint. Okay, And so that means that I'm going to go in here and select the 2.0 for my K sub Fs. Okay? And while I'm writing this down, let me talk through and kind of extract a more general principle for you for life. This isn't necessarily something that's, you know, useful on a test or anything like that in this class, but in life, a lot of times situations like this will hit you where some situation approaches and you have some information about a few cases that are in a table in a book or something somewhere, and none of them are exactly what you want, right? So then you have to make a judgment call and try to figure out, well, is there another resource where I can get some more information? Yeah, maybe, and if so, then that's a good thing to do. But what if not, and you need to come up with some good estimate quickly? Okay, you can kind of increase the number and use something that's more conservative. That's certainly something you could do. And for that reason, a lot of times there's actually some folks that as soon as they look at it and see there could be a stress concentration factor, they just use 3. Right? I've seen people do that before where they say, oh, that looks like there's going to be a stress concentration factor right there. Don't want to get into it. Let's just assume it's 3. All right? So I'm not saying you should do that. I'm just saying that's one of the ways that someone could go. If you want to be a little bit less haphazard about it, you can try to do what I just did and come up with what is the closest situation to what I think is causing the stress and why there's a stress concentration. And more generally speaking, you know, there might be other situations that aren't stress concentrations where you still have to look at it and say, what is physically most the same as the information that I have to work with? And then do your best to estimate based on that. Anyway, hopefully that helps a little bit. All right, so this is what my minimum stress is going to be, and now this does include K sub Fs. Okay, and so we'll go ahead and calculate that. It'll be 3.354 KSI. All right, and we do something very similar for the maximum stress. Okay, square root of, okay, over here I had 808.24 PSI. To that I'm going to multiply 2.7 and square it. And then I'm going to add 83 through 13.3 PSI times 2.0. All right. This also includes K sub Fs, and it ends up computing to, let me find it, 8.353 KSI. Hang on. That's without the stress concentration. I have it in here another place somewhere. 16.77 KSI. Yes, sir.
So this equation is E on page 479, but the page before in an example, to get the overall tell,
Yep.
they like added the primary and the secondary.
Yep.
And squared it, and then also used the secondary squared.
Okay. Was that a, the question was, you know, this is the equation that it has on that page, but on the previous page it has, you know, stresses where they find a resultant first, and then they use that similar to what we did for our torsional case last time. And so that is also the answer as to why it is that way, is that they are doing, I believe, I'm looking to make sure, yes, on the previous page to where they have that equation where it's the square root of the sum of the squares of the stresses, they are doing a torsional stress example. right? So they're applying a torsional load to a weld group on page 478, and that's why they had to do a resultant first before they did that. When you're doing bending cases, you just take your primary and secondary shear, take the square root of the sum of the squares, and that gives it to you. The reason for this, by the way, is that when you do primary and secondary shearing stress, the axes are always perpendicular whenever you are doing bending, whereas they are not whenever you're doing a torsional case. Okay, so that kind of eliminates one of the steps that you have to do. All right, so there are our maximum and minimum shearing stresses. What else do we need? Because we don't actually have a spot to plug max and min shearing stresses into our Gerber equation that we had up here, right? This Gerber equation. Okay, we need mid-range and alternating. Okay, so to get that, you might remember back from chapter 6, the definitions of the mid-range and alternating stresses that occur if you know the maximum and minimum. So if you're trying to find mid-range, say, what do? Average of maximum and minimum, right? So we have 16.77 KSI plus 3.354 KSI. Let me ask you a quick question. What if I had a spring that could support both tensile and compressive stresses, and my problem involved both pushing and pulling on this point? Okay, it's a little tricky because it shears, but it is important to understand that you would want to add a negative stress in this case if you had a situation like that, right? We're not doing that because we have both the same direction, but if you had a reversing, if it actually reversed direction, you'd want to make sure that that was indicated in the signs of your mid-range and alternating shearing stresses here. So go ahead and leave that there. We have this average is 10.06 KSI. Okay, that is a very important number for us. What about for our alternating component? It looks very similar, but we do 16.77 KSI minus. So you take the difference there between the maximum and min and divide that by 2. And that basically gives you how far you deviate from the mid-range stress to get to the extremes. Okay, and that value ends up being 6.708 KSI. All right, we good so far? So let me go ahead, since we've made some progress here, let me go ahead and note these values up near the top so that I can put them into my equation in just a moment. Okay, tau sub m is equal to 10.06 KSI, and tau sub a was 6.708 KSI. So what's next, you think? Okay, we probably want to do something about the endurance strength for this material, right? Which means there's a few steps to do that, right? First of all, 1018 steel. We need to know some properties for 1018 steel. And rather than spend time looking these up, let me just give these to you. And I need to tell you kind of what page these are on. This is on, let's see, A22, page 1051. Okay, and on that page it tells us that 1018 steel has an ultimate strength of 49.5 KSI and a yielding strength, which we'll need here in just a minute, of 32 KSI. Okay. Well, how do I use that when we are getting ready to find an endurance limit? Okay. Well, fully corrected endurance limit involves, first of all, finding an uncorrected endurance limit, right? And what was that? Okay. Half of what? S sub ut. Okay. But then I have to multiply all that by what? Okay. A number of factors. Okay. One of them is a surface factor. Okay. Which is almost always something that you have. The only time you don't want to have a surface factor is if you have a really nicely polished surface, which very seldom is that what you have with a weld. Okay. So surface factor. Okay. My best advice as far as a surface factor is welds are about one of the worst type of surface that you can have for fatigue. Okay, so even like when we flip back here to chapter 6, where it kind of tells you how you might go about finding some surface factors. Here we go, page 296. Okay, we probably want to pick about the worst possible thing in there, which actually doesn't make it actually kind of makes some good sense. The as forged description that's in there is going to be the thing that gives you the highest amount. Well, it's really going to be the lowest Marin factor, right? But it's the highest amount of compensation basically for a bad surface, right? So we're going to put in a factor of 39.9. So K sub A is going to be 39.9. times the ultimate strength of 49.5 raised to the exponent of negative 0.995. Okay, and when we do that, this ends up giving us 0.822. So there's my surface factor. What's next, do you think? Size factor. K sub B. Okay. To find K sub B, it involves multiplying by taking a diameter and putting it into this empirical equation that we have that is in terms of a diameter. Do we have a diameter? No. Do we have a case of rotating bending? No. So that means we can't immediately apply any of the dimensions that we have for this case to that equation for K sub B. So what do? Okay, we have to find an effective diameter. And the best place that I can advise you to go for that is on the following page, page 298. Okay. So I'll go ahead and put that right here, page 298. And it's in table 6.3. Okay. What we have for D sub E there is 0.808 times the square root of HB for a rectangular shape. Okay. We have basically something very similar here. It's just that we have two rectangles, and so we're going to want to take the weld size and multiply it by 2. Okay? So what we have here is, I guess first, before I do K sub B, let me do D sub E. D sub E ends up being 0.808 times the square root of 2 times the weld size times B. Okay, and B was 1.75 inches. Okay, so this gives me an effective diameter that I can apply into that K sub B equation. This winds up giving me 1.069 inches. All right, now I'm going to apply that to the equation for K sub B. K sub B, if we have an effective diameter of 1.069, comes from equation 620, and it's just 0.879 D. And it's expecting that number to be in inches, so since it's an empirical equation, we can strip the units out of that. And then we take that to the negative 0.107. Like that. Okay, and this ends up giving me 0.873. All right, in case you're interested, this is an equation 620, page 296. Okay. And I didn't ever write it for my surface factor, but that is based on equation 619 and table 6.2. Okay, those are the tougher ones, right? Now we're going to go look at some of the other Marin factors. K sub C. This is a loading factor. Okay, and they give you 3 options: bending, axial, and torsion. Okay, we don't have any of those, but we're going to use torsion anyway. Okay, why do you think I'm doing that? Okay, yeah, the main thing that makes that K sub C 0.59, you notice it's very different than the other ones. You have 1, and then you have 0.85, and then you have 0.59. The 0.59 that you have there, primarily what that's doing is using distortion energy to adjust the strength of the material. Okay, that's the main thing that composes that torsion factor that they put in right there, and that's basically what we need to do. So more or less, by applying this 0.59, you're turning this from an S sub E into an S sub SE, right? A shearing endurance limit rather than a normally applied endurance limit. Does that make sense? So once I put that 0.59 in there, which I'll go ahead and put these other 2 factors, I'll put 0.873, and then I'm even going to put it in a different color, 0.59. That is what converts this from S sub E into S sub SE. Okay. All right, what else do we have to consider perhaps? Okay, temperature factor. We said it's room temperature, so do I need that one? Okay, don't need the temperature factor. Reliability factor, which was K sub E. Okay, if you're assuming you want 50% reliability, which was what we said right here, then you don't need a K sub E either, right? It's just 1 if you assume you want 50% reliability. All right, anything else? Answer is no, we're good. So if we compute this, it ends up giving me an S sub SE value of 10.48 KSI. All right. .48 KSI. Okay, let's do a little inventory. So far we have tau sub M, tau sub A, S sub SE. What else do we need? S sub SU. All right. So maybe I'll even put a heading on this. This is ultimate strength estimate for shearing. Okay. So for that, there's another section here in the book that's a little bit later on. I'll need to find it. I believe it's somewhere around where they're doing combined loading. Page 325. Okay. Page 325. And they give an estimate there for the ultimate strength for shear as 0.67 times the ultimate strength tensile. So S sub SU is equal to 0.67 times S sub UT. Okay, and that ends up giving me 33.165 KSI. Okay. That looks like it's everything that I need to find my factor of safety for using the Gerber criterion. So now we got to do some plugging and chugging. Okay. N sub F will be equal to 1/2 of, okay, here we'll put in S sub SU, 33.165 KSI over tau sub M was 10.06 KSI. Okay, and then I'm going to take that and multiply it by tau sub A, which was 6.708. It very well might be. Let me verify. I may have made an error whenever I first... It is. I don't know if I neglected it or if I accidentally erased it or something. Anyway, I didn't get it on there, and it should be squared. Okay, 6.708 KSI over S sub SE. Okay, S sub SE was 10.48 KSI. And then here we've got -1 plus the square root of 1 plus. Here I have 2 times tau sub M would be 10.06 KSI. S sub E was 10.48 KSI. Got all of this over S sub SU, which was 33.165 KSI. And then sigma A, which was tau sub A, which was 6.708 KSI. Okay, and I believe all of that was squared. All right. And what you are left with there, if you actually do this whole calculation, it'll tell you that your fatigue factor of safety is 1.314. Okay, and keep in mind, this is a factor of safety, assuming that what you're after is infinite life. All right. What if you got down to a factor of safety below 1? What would the consequence be? Okay, you would be less sure, right? It's, you know, at that point you'd be less sure that it would last forever. Okay, but it may not mean that it would break instantaneously. All right, we've got a couple of other small tasks to do here, because generally whenever you do an evaluation for fatigue, the other thing that goes along with that is an evaluation for first cycle yielding, right? To kind of make sure that you're not going to have something like that. And let me go ahead and say that doing the evaluation for first cycle yielding often does not include the stress concentration factors. Okay, so I'm going to kind of do this part of it first. What would you say that process would look like with no safety factor, or with no stress concentration factor? Okay, yeah, what we'd want to do, this is for no safety, keep saying that wrong, stress concentration factor. Okay, you take the stress that causes failure. What would that be? Okay, yielding stress, but remember we're dealing with shears, right? So I take the 32 KSI and multiply by what? Okay, distortion energy theory would have me divide by 0.577 to get what the equivalent value would be for shearing. Okay, and then you put that over the stress that you're actually applying. Okay, and the stress that we're actually applying can be found with a calculation very much like what we did down here for tau max, with one exception. Right? What would that be? You take out the stress concentration factors. Okay, so let me copy that. Okay, and I do away with 2.7 that I have right here and the 2.0 that I have right there. Okay, and that allows me to find a stress concentration factor, which is 2.21. Okay. Now what if I want it with the stress concentration factor? Not much different. All I got to do is take what I did here and instead of removing those stress concentration factors that I had here, I leave them in. Okay. Which, by the way, we already did that calculation once, right? What was this whole square root right here? Yeah, that square root was 16.77 KSI. Okay. So anyway, if you put that in the denominator with 32 KSI times 0.577 in the numerator, this results in about 1.1. All right. And remember, I'll mention it again. The reason that you can sometimes do away with your stress concentration factors if you're dealing with ductile materials and static loading is that, which that would kind of be the case for the question of first cycle yielding, is that if it yields a little bit, right there at the really highest values of stress, it's not that big a deal, because when it yields, everything will deform a little tiny bit, and it'll end up distributing those stresses out to other material that's also helping to carry the load. So, all right, any questions before you go? Have a very happy weekend.